Okay, so this is worksheet 21. So we're going to talk about critical values and critical points and what's the difference. Maximum points, inflection points. We've hit this before. We're kind of hitting this from a different angle. I'm going to make sure that you have some of the basics down, and then we're going to head into some exercises. So the overarching theory works kind of like this. First of all, you have yourself a function. Well, maybe you have an axis if you're lucky. All right, and you have, here's your function, something like that. And given this function, you can break it up as follows. You can say, hey, here's a local min, here's a local max. When you are going, when you're decreasing your, so here's your function f. When you are decreasing, you know that between here and here, f prime will be negative. And when you're increasing, f prime is positive. Okay, so when you're at a max or a min, it's required that f prime equals 0. Now there's a problem in that here's what you have to be aware of, that f prime can be 0 in this kind of situation too. Let's say you have y equals x to the 5th. Y in that case, y prime at 0 is 0. Y prime is what? 5x to the 4th. Y double prime is 20x cubed. Y triple prime is 60x squared. Y to the 4th derivative is 120x. Y to the 5th derivative, like y 5 derivatives, is just 120. And y 6 and beyond are all straight up zeros, okay? But all of those derivatives are 0. So it only tells you that you have, if you were to draw a tangent line right there, it would actually be a tangent line that cuts the curve, which is kind of, seems like you're cheating. But when you have 0 concavity, then this happens sometimes, right? So you have a horizontal tangent line, and that doesn't guarantee that you have a max or a min. It just guarantees that it could be a max or a min. So the implication runs one way and not the other. So for example, if you have a max or a min, which we're going to call a critical point, so those two things bundled together is a critical point, that implies f prime is equal to 0. Similarly, if you have a point of inflection, the second derivative is 0. But it does not go the other way. No. These do not go the other way. But it is strongly likely to go the other way. So that is why when we are searching for maxes and mins, or searching for points of inflection, we take a derivative or two. So we have f prime equal to 0, find x's. And these guys I call potential maxes and mins. Or if you do it on the second derivative, you get x's. After you set second derivative equal to 0, you get the x's. I call these possible or potential. Any word you want, but the point, possible points of inflection, potential maxes and min. You put some kind of flavoring word in there to make sure it is understood that you are on the hunt for maxes and mins, or you're on the hunt for inflection points, but you haven't fully determined if these candidates have passed the test. Okay, so that's just your first step as you're looking for them. All right, so we'll get into that a little bit more in a second. All right. There's a small difference between critical values and critical points. So for example, I'm just going to make something up. Let's say this is at -3 and this is at -3, 4. I will call this thing here a critical point, whereas I'd call just x equals -3 a critical value. So if I'm just going to make a list of the independent variables, usually x's, then I would call them critical values. Once they're joined with their partner, then they're critical point. Okay, so that's the difference. So just to make that clear, that way if the teacher just wants you to find the x's and not have to go through and plug the points back in, then the instructions will just say critical values. Okay? And why do we have a different term for critical points versus maxes and mins? Well, you haven't yet classified them when you first find them. You find your potential critical values, and then you're going to look to see whether they generate maxes and mins, points of inflection, or maybe it's something else, you know, but usually it's maxes, mins, or points of inflection. There's other weird things that I don't think we're going to deal with at all, but you can build weird stuff. Like you can put cusps and things like that, where, well, then it's not going to be 0. You could, for example, make a function like that. But if we're dealing with continuous functions, we don't have to worry about that kind of stuff. Okay, so let's say, in this diagram I need to also review concavity, just real quick to make sure everybody's clear what's happening with concavity. So if I split this guy here and say here, this part here is going to hold water. In other words, it's cupping up. It's making a sort of a smiley face. And so the second derivative is positive, and the other ones are spilling water. So the second derivative is negative. And as we've already shown, well, just by graphing it, if you try to put a tangent line on a point of inflection, then you'll end up with a situation where you do end up cutting the curve. Okay, I think you know where I meant to put that. So it wasn't really working out that well, was it? Anyway, you know what I meant to do. Okay, so that's the concavity thing. So when you're looking for points of inflection, you're going to set the second derivative equal to 0. And I want you to notice what's happening now. We have in this diagram a max and a min. So we know f prime equals 0 in both cases. But when f prime is 0 but f double prime is less than 0, so you're spilling water, it means you have a max. If you have f prime greater than 0 while f prime is 0, then you have a min. So that's one really easy way to classify the maxes and mins. This is called the second derivative test. And let me just sort of type that out for you, because again, that implication only goes one way. You have to be careful. Okay, so the second derivative test does not always work. But when it does, here's what we do. We found some x values, critical values, from setting f prime equal to 0 and solving. If we check out f double prime at an x value and it's negative, we know we are concave, what? Down. So we have a max. And of course, vice versa. I'm not going to type it all out, but it's exactly the same thing. If we check out f double prime at an x value and it's negative, we know it's concave down, so we have concave up, so we have a min. But only if we already know, this only happens in the context of we already know f prime is 0. How can this go bad? We already explained this. Warning. Maybe f prime is equal to 0 and f double prime is equal to 0 also, then this trick doesn't work, because you're dealing with some kind of there's more zeros hidden under there. So you have to keep looking for those zeros for derivatives until you get to a point where the next level down, it's not equal to 0. Okay? So what do we do when that happens? So we have a second trick. We will have just the first derivative test. First derivative test is less fun, but it's actually honestly more likely to work in a wider variety of cases. There we go. So f prime equals 0 at some x value. So we just check out f prime just before and just after this x value. Okay, so here's what it looks like graphically. So we've got ourselves some kind of function, and we have f prime is equal to 0, and we want to see if it's a max or a min. So we just look right before. So if this is like a 3, then we look over here at maybe 3.1 and 2.9. Usually just adding and subtracting a tenth is more than good enough for the vast majority of exercises you're going to run into. And if you're going to calculate this on a computer, you can pull up, you know, your calculator, or you can pull up Google or Wolfram Alpha or whatever, and let some computer do it for you. What you're going to find out, if for example here f prime is negative, and then it's 0, and then f prime is positive. So I want you to imagine down, flat, and up. And when you think about that, that means min. If it's negative, 0, and positive, that means min. But if the pattern instead is positive, 0, and then negative, then what you have is a max. It's really that simple. Just know, are you going negative 0 positive or positive 0 negative? And you're not going to get 0 0 0. You're going to get a sequence of positive to negative. Now, you could get positive 0 positive. Well, what does that mean? Well, okay, let's think about that. Those two more possibilities. You could get positive. What if you get positive 0 positive? Then that point you were sitting on is actually a point of inflection, right? So f prime is positive, 0, and then positive. It's just a point of inflection like you'd see at y is equal to x to the 5th, x to the 7th, and so forth. And similarly, if you go negative 0 negative, you just sort of flip that thing around. So if you had negative 0 negative, again, it's just going to be a point of inflection. So f prime is negative 0 and negative. Then you're just going to also have a point of inflection. So that's why, honestly, the first derivative test is really cool, and it's sort of not given the credit it's due, I think, because most calculus classes, we start by teaching people the first derivative test, and then we say, hey, we're going to make you so much cooler by teaching you the second derivative test. And it's like, yeah, now it fails sometimes. So what did we gain? Except that we gained in comprehension of how these derivatives fit together. And if you've got the second derivative laying around anyway, you may as well go ahead and put it to good use. Okay, so I think that's the theory, and we can go into some examples. Yeah, let's have some examples now. Okay, so these kind of exercises where you have some kind of curly thing sitting on the page, and you're supposed to classify all the maxes, mins, and points of inflection. Okay, so it's easier for me because I've got myself a computer that I can make a straight line segment, but in your mind's eye, you sort of pass this along until you find, aha, there we go. This should be a max, min, or one of these weird points of inflection. I think I'm going to just call that a point of inflection. Let's see, there's one here. So this first red line is one of those weird points of inflection. So there's other points of inflection, but I'm just going to sort of work my way through all the examples here. And then I've got one of these guys here. I think that's it. I think those are all the maxes and mins. But you see, one of these guys, they got in there when they kind of, well, I mean, they should have. But this is one of these weird ones. This actually is a point of inflection, even though it's got a horizontal tangent line. This guy's going to be a max. This guy's a min. This guy's a max. Okay, now the next thing is a little harder, which is we want to see where the concavity changes. We want to see where we split from sort of, you know, like actually I'm going to draw a circle. See if this helps. I want you to imagine that you have a round circle and you're going around and you have to sort of be on the inside of this curve. At some point you have to flip. If you want to be on the inside of the curve, you have to flip to the other side. So I'm going to see where is that point at which I have to flip over, and it's right about maybe here. Okay, let's see if that works. So I'm concave down when I'm spilling water right up to about here, and now I'm going to start being concave up, and it's going to split again roughly like here. All right, and then let's see, I'm going to use this thing like I'm sanding the inside of this guy. And this point of inflection here happens to have a horizontal tangent line. Like I said before, it's kind of a fluke, but there you go. And then if you just keep doing this, just in your mind's eye, think, what would I do if I had a big magic circle? And I'm just, you can change the size of this circle. It doesn't matter what size it is. Just kind of think, I'm going to sort of buff the inside of here. And I'm going to move up here. I'm going to buff the inside of this circle here, and now I'm going to go up here and buff it. Again, it's sort of, maybe you want to make the circle smaller so you can fit in here. Then you're going to come over this way. Then you're just kind of, imagine you're sanding it. And at what point are you, you're switching from, so you're on the outside here, the rain is going to fall off this way. And so inside, you're on the inside of the umbrella versus you're on the outside of the umbrella. And here you're on the inside of the cup versus you're on the outside of the cup. So let that be a little bit of a thought experiment for you. And if you can get the points of inflection, then telling whether it's concave up or down is not a problem. So this is concave down, concave up, concave down, concave up. This whole piece is concave down, concave up, down, and up, like that. Okay, so that would be the algebraic thing. And beware of other little tricks that happen, like cusps. Cusps are, you can have a max there, but there is continuous. So let's just say at a cusp, let me just give this thing a name because you have one in your worksheet. So here we have this kind of structure. At a cusp, you have continuity of the function. However, the function is not differentiable there. So just beware of that. So you can label that as a max, but you can't use like a second derivative test on it. You can just say, hey, I go up here, I reach a max, and then I go down. Okay? Okay. So let's try an example. What if we have a function like this and we want to find the critical points and the points of inflection for this function? So we're going to want to take a derivative. So we're going to do derivative of the first times the second plus the second derivative of the second times the first. And this guy is just like not a big deal, but we can factor that. Well, we may as well take x squared out. E to nothing is going to be 0. Nothing's going to work. But we have critical values are going to be x is equal to 0 and minus 3. Okay? And so we can deal with that later. We're going to hold off on that until we look at the second derivative. So based on this guy, we're going to take the next derivative. So e to the x times the derivative of the stuff inside here plus the other piece we need. And so we end up with x cubed plus 6 x squared plus 6x, which again, there's an x that comes out. And we have a critical value at x equals 0, but we also are not sure if it's just going to actually end up being a point of inflection. So we get to investigate this one. So this is going to be a little bit more fun. We're going to have to look at, so we have x is equal to 0 is one of the things we have to consider as a possible point of inflection. and we want to solve for this, just make sure we know when this guy is equal to 0. So we use x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, which is minus 6 plus or minus the square root of 12, which is 2 square root of 3 divided by 2. Okay, it's not as bad as it looks, so it's minus 3 plus or minus square root of 3. So we have minus 3 plus or minus square root of 3, and let's see what happens. We have all this information, and we have to kind of bring it all together and see what's going on here. Okay, so we have, let's take a peek on Desmos or Wolfram Alpha to see what's going on with this graph, because I'm kind of curious and I want to get a hint here. Okay, so it was e to the power of x times, and what was my function again? I said just x cubed. Okay, so that's pretty cool. So we see that at 0 there is in fact a point of inflection, and at roughly -3, well exactly -3, we have a min. And so we're going to look for an inflection point to be right around here. Wonder if there's anything else we need to be aware of in this plot, because you know our algebra told us that we had 2 possible points of inflection, and I'm wondering if we messed that up. Maybe we did, maybe we didn't. So maybe there's an inflection point here and an inflection point here. I bet that's what's going on. Okay, so it's on either side of the 3. So that's what it looks like. So that's good. My intuition is now reassured, so I'm going to go back to working the problem and try to sort of make this thing work out. Okay? So what are we doing? Okay, so what I want to do is I want to lay this out on the screen a little differently. So I'm going to just pull all this stuff over and shrink it a little bit so that we can have more space to talk about this problem. All right, and so we're going to have some kind of graph. We need to know what the values of f are. At the very least, we need to know what f is at 0, -3, -3 plus square root of 3, and -3 minus square root of 3. We need to know where all that's happening, what's going on here. E to the 0 is 1, but it's times 0, so we get a 0. And -3 cubed should be -27, so you're going to get like -27 times e to the -3, which isn't going to be as big as you'd think. So let's pull up a calculator and figure out what's going on. Pretend that we don't have Desmos, but we've got Google, because we just want to figure out what is going on here. -27 times exp to the -3, and I think Google can tell us what that is. So it's about -1.34. And then we have to evaluate this function in 2 more places. So honestly, let's go over to Wolfram Alpha, because Wolfram Alpha is really good at this sort of stuff. I'm going to say evaluate x cubed times e to the power of x at x equals 0 -3 plus square root of 3 and -3 minus square root of 3, and hopefully it will just give us all those values we wanted. Except when it does this nastiness and it gives us, you see, here's the problem. It actually won't do it numerically. So if you just put the decimal point at the end of these guys, it'll think you want to do this all numerically. So I'm just going to put decimal points at the end of all the numbers so they don't interpret them as integers. And that should take care of that problem. And hopefully I'll get something doesn't look right. I don't think it worked right. E to the power of x. Huh, that's weird. Let me figure out what's going on. Okay, to be honest, I have absolutely no idea why Wolfram Alpha refused to do this, but usually it works like a charm. So I'm just going to try this. It seems like if I give it one at a time, it'll work. So it's going to be negative 0.573, which is good enough for our purposes. And then I'm just going to do the same thing with a negative in here. Negative 0.933, and there's one more problem. You may not know exactly where plus and minus square root of 3 is, so I'm just going to find out where that is. That's about negative 4.7, so I'm going to put right here negative 4.7. And what about if I flip that sign around? It's going to be negative 1.3. Okay, that's a lot of messing around, but we kind of have to do that if we want to plot stuff. So here is our 0, 0, and then at negative 3, it's going to be like negative 1.34. So that's going to, it looks like it's going to be our min. It's definitely the min of these things that we've dealt with so far. And then at about negative 1.3 and negative 4.7, so in any case, it's going to be equally spaced vis-a-vis the 3. You know, sometimes my computer is just really nasty to me. I don't know why the screen is not showing up. My axis disappeared. Hopefully you can see that now. So the point is equally spaced on the right and the left of the 3 should be our points of inflection, and the one that's closer to the origin is going to be like about here, and the other one's going to be like here. That's what it's saying. So it's guessing, we're guessing that those last 2 points, that these guys are probably points of inflection, and these guys are probably, who knows, like we have a better idea because we looked at the graph. But so far this is what we have. We just know that we have potential, maxes, mins, and points of inflection, and we've sketched them on the graph. Okay, so far I'm just going to say what we did. So far we took 2 derivs, found possible max, min, and PIs, found their y values, and plotted them as a starting point. Yay! All that work, and we've just barely started. Now we get to do some more calculus. Now what we're going to do is take those points and see, hey, we have options now. We have options. We can classify critical points based on first or second deriv tests. Okay, now since we're not really sure what's going to happen here. Like, this isn't your normal polynomial. This is kind of nasty because we have an e in there. So what I'm going to suggest is that we break up the domain and we test the first derivative just so we know, are we increasing or decreasing? Suggest first deriv test because this problem looks nasty. Okay, so that's what I'm going to do. All right, so what I'm going to do is I'm going to pick a point between each of my other points. So I'm going to try f prime. I'm going to try f prime. I'm going to try f prime at, well, I'm going to try getting my pen back first. Oh my gosh. Okay, so I'm going to look at x, and I'm going to look at f prime at those x values, and I'm going to strategically pick them so that they're between all these points. So I want something that's positive, so let's try 1. I want something between 0 and negative 1.3, so I'm going to pick negative 1, so I can pick like this point here. And then between negative 1.3 and 3, let's try negative 2. And at negative 3, let's see, the derivative is 0. So something between negative 3 and negative 4.7 would be, say, negative 4, and then something to the left of negative 4. So if we just pick these values, they're conveniently, strategically placed in between these points at convenient places that are easy to calculate. Let's go ahead and try Wolfram alpha. We're going to kind of press our luck with this, but maybe it'll work this time. Okay, so I'm going to ask it to evaluate the derivative. Okay, so I'm going to ask it to evaluate e to the power of x times x cubed plus 3x squared at x equals negative 1, actually 1, negative 1, negative 2. Might as well just throw them all in there and see if it works. Well, it did work, except it gave me everything in terms of actual real-world answers, which I don't really care for at the moment. I just want to know if it's positive or negative, honestly, but it's easier to tell if I just do it this way. Okay, so the derivative over here, f prime, is positive. Let's see. And then we get positive, positive, 0. 0 is the negative 3 that we didn't write, and we have 2 negatives. Okay, so now that we know that the first derivative is positive or negative between these different values, now we can figure out what's going on, because we know from 0 onward it has to be increasing forever. All right, and we know that between, let's say, negative 1.3 and 0, we know that it's also increasing, which means this guy's fate is sealed as it's just increasing, so it has to be some sort of point of inflection. I haven't drawn it very well, but it's some kind of point of inflection. Okay, and now we know that between here and here, it's also increasing. So this has to be some other kind of point of inflection, because you go increasing, increasing, increasing. And these guys are decreasing, decreasing. Oh, come on, stupid computer. Here we go. Decreasing, decreasing. I don't want a line. Computer, please. All right, so you have a min here because it's decreasing, decreasing, must have a min, and then plus, plus, plus. So all the other things that we've classified as potential points of inflection, they must be, because they don't turn around. So you go negative, negative, you're going down, down, so that must have meant you went through a point of inflection. And then you hit a min because we actually had the derivative being 0, but we went from the first derivative was increasing, I'm sorry, it was decreasing and then it was increasing, so that must be a min at -3 and so forth. And so now we can go back to Wolfram Alpha again and see what this looked like, or Desmos. Did we graph on Desmos? And now we can verify that we actually did this thing correctly, because here's -3, it's a min, and right about here must be a point of inflection, and right around here is our other point of inflection. Okay, so hopefully that is useful to you. Okay, so let's say we have one more type of example, because you're gonna have to work on the last question on your worksheet. So let's say you have a function, and first of all you have to find out whether your function is actually is f of x continuous and differentiable. If you don't answer that question, then this exercise doesn't make sense. But if you are guaranteed that the function is differentiable, then you can pull the following stunt. You can say, well, somewhere between x is 2 and 3, I must have a zero derivative, and somewhere between 5 and 6, I must have a zero derivative. So how do you classify them if they're maxes or mins? So here in the first part of the function, it's increasing, then it's decreasing, then it's increasing. You literally just look at the sign of f of x. So the function has to go increasing, decreasing, increasing, and somewhere in here f prime is going to be 0. So that means somewhere in here there's a max, and somewhere in here there's a min. Now this doesn't mean that there aren't other such things happening. There's nothing telling you that there's not additional wiggles going on that are hiding between the sample points. So there could easily be more. There could be, who knows, maybe unbeknownst to you, between 1.5 and 1.7, maybe it goes negative again. Okay, you don't know that, but at least you're guaranteed the existence of at least one max and at least one min, and you have a very similar situation in your worksheet. So, okay, hopefully that you should be now ready to do the worksheet and the quiz.